Hello, everyone. It's a pleasure to be here. So today I'll be talking about some work that I've done before I joined DeepMind, when I was a member of the Bayes Group. So it's a joint work with my fellow colleagues Dmitry Kondrashkin, Anton Osokin, and Dmitry Vetrov. So today's lecture will be an intersection between three different fields of machine learning, subfields of machine learning. So the first one is representation learning. This is a field that has recently gained a lot of popularity. It is very, very tightly connected to deep learning. And another thing we'll be talking about is Bayesian nonparametric. So today, I think you had a couple of lectures on Gaussian processes. They fall into this kind of subfield too, but the kind of Bayesian nonparametrics I will be talking about will be slightly different. I will focus more on Dirichlet processes. And in order for this to work efficiently, to have a practical algorithm, we'll also mention a bit of variational inference, which you have already had a lot of lectures about, I think. So let's begin with representation learning, just to remind ourselves what it is and why it is worth thinking about it. So imagine you want to solve a machine learning problem, a practical problem. So every machine learning problem starts from data. So you have some data. It can have very different modalities. It can be images, it can be text, it can be sound data, it can be anything. So once you have data, well, you choose a machine learning algorithm. Depending on your task, depending on other requirements that you have, you're choosing an algorithm. And then you see what happens. If it's a supervised or even a supervised learning problem, you can measure some metrics, see how well your algorithm does, maybe tune something in the pipeline, and that's how it works usually. But there is one step missing that is maybe clear from this slide, from this unusually long arrow. Can anyone guess what is maybe missing here? Preprocessing. Well, to some extent, that's true. That is true. But what else, or how else we can? What, sorry? Yes, exactly. So it is very important. The whole outcome of this pipeline depends a lot on the features we're running our machine learning algorithm on. So you probably know that if you take, let's say, an image, if you have a large collection of images, you take one of them, and you try to see what are the nearest neighbors to this image in your collection, and you use the representation that you use by default to store this image, your RGB values for every pixel, then very likely you will get images that are just by color similar to the target image, not semantically similar. If you just permute the RGB channels in one of the images, it may get either closer or further from the target image, but this does not say anything about the content. And from deep learning, we also know that one of the great successes, for example, modern convolutional networks, is that they encapsulate this step in the model itself. So neural network is able to extract good features, but on top of the neural network, you usually have something very simple, such as a linear classifier or a linear regression. This means that if you have a good feature representation, you may not need to have a sophisticated machine learning algorithm at all. And in today's lecture, we will focus on representation learning for text data. In particular, we will learn representations of single words. So you may formulate this problem in many different ways, but for us today, the goal will be the following. For every unique word in our text corpus, we want to find such an embedding, such a high-dimensional vector, that words that are semantically similar, semantically close to each other, also have close embeddings in this latent space. So in this very simple example, we have a small text about elephants, that they live in Africa, that they are mammals, and so on. And if we were to extract word embeddings from this small piece of text, we would get something like this. So here, the word animals is closer to word mammals because they're kind of both describing, the biological structure of elephants. words such as forest and bush are also close to each other because they describe where do they usually live. And Asia and Africa are also similar because these denote some geographical, names of continents, basically. And there is a very popular model called skipgram that maybe even made a small or not so small revolution in natural language processing some time ago that does exactly this. And let's see how exactly it extracts word embeddings. So for every word in our corpus, we learn two embeddings. One we will call input embedding, and another one we call output embedding. So output embeddings, we will focus mostly on input embeddings, and output embeddings are only needed for some technical purposes. You may not focus on them too much. So for every word, we have these two vectors, and how exactly do we learn them? So first, we start reading the text we want to train on, and imagine at some point we are focused on this word. We read this word, mammals. So what we do, this is our current word, and we somehow have to choose, the context for this word. For simplicity, we can think of it as all words that are in close proximity to this word. For example, 3 words to the left, 3 words to the right. This will be the context of this word denoted by Y. And skipgram is a very simple word prediction model. It is so simple that it's not even a language model, even though you can use it for language modeling, but that's not the purpose of the model. So all this model is trying to do, it is trying to predict these context words from the current word X. We make another simplified assumption that all these words in the context are independent. We ignore their order. We just want to be able to predict them. And the prediction model is again very simple. It's just a softmax. Basically, the probability of a word in the context of another word is proportional to the exponentiated dot product between the input embedding of the current word and the output embedding of the context word. So we apply this formula for every context word, ignore the order, and this defines the model. So it may be unclear how such a simple model can learn good word embeddings. Why would this work? Because this looks very simple. But actually, skipgram model is based on so-called distributional hypothesis. So what it is? So we believe that similar words, semantically similar words, should appear in similar contexts. Well, what does it mean? Imagine that someone already learned the output embeddings for us for a second. Someone gave them for us. Then, if 2 words appear in the same, in similar contexts, so similar words appear in their contexts, then their input vectors should also be close to each other, because the model should be able to predict the similar context from both the input representation of one word and the input representation of another word. So it makes sense. Of course, no one will give us the output representation beforehand. We will learn them jointly, but that's sort of the cartoon explanation of why this is actually working. And skipgram is trained in a very simple manner. We simply scan the text. We look at some of the words. We try to predict their contexts. We compute likelihood of this prediction, of this collective prediction. We compute the stochastic gradient based on this local likelihood and perform the gradient update. Then we move one word further. Again, try to predict the context, compute the likelihood, estimate the gradient, make a gradient update, and so on. So skipgram is a nice model. It learns high-quality, semantically rich embeddings. Maybe you have seen this. Images where you have a vector of the word king. You subtract the vector of the word man. You add vector of the word woman, and you get vector of the word queen. I personally don't believe in this. And recently, a paper has been published that criticized this a lot for maybe not too strict methodology in discovering these kind of analogies in word embeddings. But nevertheless, the representations that you learn are quite good, and you can use them as a building block for a bigger application. So if you want to do, I don't know, whatever, information retrieval, text summarization, some upstreaming natural language processing tasks. If you don't want to learn everything end-to-end from scratch, if you're limited in your data, using word embeddings as features for words is a very good idea, especially those produced by skipgram. So so another interesting feature of the skipgram model is that the gradients that we just computed, they're very sparse. So I'm not explaining why they're sparse in this lecture. You will have to believe me. But basically what happens is that we can compute only our gradients will be non-zero only for the input representation of the word we're currently looking at, and a small subset of other words. We won't need to compute the actual gradient of the softmax model I just described. And this sparsity allows us to train this model in a very fast fashion using maybe even in parallel. So for example, many of you have laptops on which you can train a high-dimensional skipgram model on the whole Wikipedia that is maybe, I don't know, 20 or 30 gigabytes of raw text data. And you'll be able to do this in tens of hours, not in days. There is no way you can do this on your personal laptop with a recurrent neural network unless you have an access to an external, very powerful GPU. And even then, I'm not sure. And this efficiency allows to process much more data in a given amount of time, and the more data you're training on, the better results you get. So this is, I think, is the secret of success of skipgram. So, okay, I just described you a representation learning method, and well, basically, are we done now? We have a good model. Why do we need to do anything else? Can we just keep using it? And the answer is probably no. So look at this picture. So here, what I did, I trained a 300-dimensional, that's a fairly high-dimensional model, on the whole Wikipedia. And I took the word apple, I took the 20 nearest neighbors of this word in the learned embedding space, and I applied TSNE just to put this on the 2D space. So does this kind of embedding space looks good? Do these results look good for you? No, why not? Exactly. So what happened is that for some reason, even though we trained on the whole Wikipedia, and that's a fairly big and representative text collection, skipgram model only learned that Apple corresponds to an American company making iPhones. It doesn't know anything about fruits. It doesn't know anything about the recording company, also called Apple. It doesn't know anything about this. And that's a serious problem, because effectively, if we use these representations, for any of the applications that for some reason requires knowing all meanings of the word, it may not work too good. Another situation that might happen with skipgram is that for other words, it will discover that they have different meanings, but these meanings will get all mixed up in the single representation vector, and sometimes in a very uncontrollable way. So there is no way to ensure that when they do mix up, all the meanings will be covered, or they will be covered in a reasonable kind of proportions. So why is this happening? This is happening because our natural language is, just by some of its natural properties, is very ambiguous. Many of the words have different meanings. There is a very simple thing such as homonymy, so some words they're spelled exactly the same, but the meanings are completely different, doesn't have anything in common. Or different parts of speech may be used in slightly different contexts and may have different meanings. Or there is slang. There are many reasons why same words may mean different things. And here you can see an example of what it can be. So for example, this word mammal that we had in this short piece about elephants has a disambiguation page on Wikipedia. So these disambiguation web pages, well, they contain a list of senses or meanings that Wikipedia editors agree on. So if they think that all these meanings, well, these words have more than one significant meaning, they will create a special web page and list the most kind of important meanings. And you can see that even for mammal, which is to me a fairly kind of, well, simple word, apparently there is a mammal rock band, there is a film called Mammals, there is the Mammals, another band. basically, we can get confused. But this is simple. Look at the word bank. So this web page is so big that I couldn't even place it on the slide. So bank can be, a river bank. It can be a financial organization. It can be a storage of something. Some of you have power banks with you. Bank can be a surname. And we cannot discard any of these meanings from the word bank if we want to process natural language in all of its richness. And Dmitry, as I understand, Dmitry Petrovich already proposed kind of a solution for this problem, and let's briefly revisit it. So what we can do, if we know that same words can actually appear in the text in different meanings, we can assume that actually there is a hidden variable which we did not observe, but which would explain otherwise this ambiguity. For example, so we could assign for each word in the text a hidden variable z, and this hidden variable would tell us which of the meanings is used in this particular context. We can try to adapt skipgram to this scenario. Then we will need to learn not just a single input embedding for each word, but basically as many as we believe there are meanings for words. So for now, let's assume that there is a single fixed number of meanings for each word, let's say 3. This means that we learn more than one vector. We learn 3 vectors for each word. And every time we want to make a prediction then in the skipgram model, we will have to explicitly say which of the meanings we are using. So for example, we will have to use a specific vector from this table. How would the latent variable skipgram look like? Well, it will not look much more sophisticated. It's the same softmax prediction model, except that now we have this additional variable z on which we condition when we're making predictions, and we use z simply to index to find the right word, the right embedding vector. And same with predicting all words in the context. We again believe they're all independent. We only think that they're all produced using one sense of the word X. And if so, we can define something like a mixture model of word context. So we can take for each word, we can take all contexts in which it appears, and say that these contexts are generated from a mixture of different meanings. So if you're familiar with mixture models, especially with Bayesian mixture models, usually the generative process looks like this. So on the top, we have for each word, let's focus on one word, we have a Dirichlet prior distribution with some parameters alpha, from which we generate the prior probabilities of word meanings. Then every time we want to generate a context of a word, we sample a word meaning using the categorical distribution parameterized by these prior probabilities. And then we use the softmax model to generate all context words. So even though skipgram is not a generative model, we can assume the following generative process. And by the way, let's see if you all really learned this. Do you know what is the relationship between these two distributions? Yes, they're conjugate, and we'll use this fact. Okay, good. So once we define the model, let's see if we are able to train it, because we introduced something that was not originally in the skipgram model. So what do we have? Let's first classify what variables we have. So first we have our observed variables, words and contexts. Then we have hidden variables. For each of the contexts, there is this zi meaning that was used in this context, and global variable spy indexed by the unique words in the dictionary. We also have just parameters, our input representations for each word and for each meaning, and still output representations for each word. So normally, as Bayesians, we would want to optimize directly the marginal likelihood, the likelihood of our data under our parameters with all the hidden variables integrated out. But as always, in all interesting models, and this is no exception, we are not able to compute this integral analytically, nor we are able to optimize it directly. So, and as we know, in this situation, we usually have to resort to some kind of approximate learning method, and a variational and one of the most kind of practical and computationally efficient approaches to this would be to employ variational EM algorithm. So, if we are going to derive a variational EM algorithm, we need to choose the parametric, or at least the family of our posterior approximations, of our variational approximations we will be using to approximate the true posterior over word meanings and meaning probabilities. So as often, because it's the simplest choice and often it is enough for, at least for practical applications, we're choosing the fully factorized approximation. So we're saying that the family in which we'll be looking for the best posterior approximation is fully factorized. So for each word, we think that all probabilities over meanings are independent, and same for all meanings of the words. Even if these words are close together in the text, we assume that we're making judgments for them independently. So once we define the posterior approximation family, we can derive a variational lower bound. As you probably know, it can be written in many different forms, but for now it doesn't really matter. We will use this form, that it's an expectation with respect to the variational approximation Q of the logarithm of the joint density minus logarithm of the variational approximation. And now, if we want to keep the effectiveness, the speed of training of the skipgram model, we will have to derive a stochastic optimization algorithm to train this model. So let's see how we can apply our knowledge of stochastic variation inference to derive such an algorithm. So first, we will have to let's assume that someone already gave us the variational approximation with respect to pi, to meaning probabilities. Then we can compute the optimal Q of z, the optimal variational approximation to optimal variational posterior over word meanings used in each context. So for that, we simply take the lower bound, fix Q of pi, and optimize with respect to Q of z. Basically, what it means that for each context, we have to perform word sense disambiguation. So we will have to guess what, given our current understanding of the model, in what sense, in what meaning has this word been used in a particular context. So one can derive the standard formula for variational update, and you will get that this distribution is a categorical, is a discrete distribution, and the probability for each meaning has basically this form. This form. So what do we have here? Here we have an expected, basically what we have here is the expected probability of the meaning, and how well does this meaning predict in the context. So the balance between this kind of expected prior and the likelihood defines the posterior probability for each of the meanings. Then we take the optimal posterior over z and plug it back to the variational lower bound. And the new bound we get after plugging in Q star, the optimal Q of z, is a bound that is tighter than the original lower bound, because clearly we're using the optimal Q of z. Then, after we have done this, we need to rework a bit the variational lower bound to make it, a bit more friendly for stochastic optimization. And for this, we need to guess, or maybe not guess, we need to first make a few observations. So first, Q of pi for each word will have the Dirichlet form, because, as we just discussed, Dirichlet in categorical, categorical is a conjugate. Dirichlet is a conjugate prior for categorical. So the posterior, the approximate posterior, given by minimization of the Kähler divergence, will also be Dirichlet distribution. And since we know that Dirichlet distribution is parametrized, is parametrized in a certain way, now our lower bound is a function of numeric parameters. Previously, it has been a function of of distributions now, which is maybe a bit tricky to optimize over. Now it's just a function over a few parameters, over parameters of all the variational digital distributions and word vectors. And if so, we only need to rewrite it as an expectation with respect to a data point to derive a stochastic algorithm. So basically, what we can see is that effectively we have a sum over all contexts in our corpus, and we can interpret the sum as simply as an expectation multiplied by the number of contexts n. So we can apply the same skip-gram stochastic gradient optimization, the same stochastic training algorithm as used in the skip-gram, except that now we have more than one meaning for each word. So we will have to compute this weighted skip-gram prediction, where the weight for using each meaning, where the weight is defined by this optimal distribution Q star, Q of z. And the other term is the standard minus scale between two digital distributions. So we also know how to compute it even in the closed form. And let's see how the training algorithm changes. So as before, we're simply simply reading the text sequentially, one word by one. And imagine now we look at this word. So we assume that we kind of sampled this word and its context from the whole collection of words. Then we need to decide in which sense or which meaning has been used in this context. We already have a formula for that, so we simply need to compute this distribution Q of z. And then we update our word embeddings using the weighted skip-gram prediction model. So we're training the same, you can think of this as training the same skip-gram model. It's just we are selecting on which context we're training each of the input embeddings. And we also need to update parameters of the Q of pi, of the distribution over prior distribution over word meanings. So here again, we can derive a gradient of the lower bound with respect to these parameters. And we're quite lucky because we're able to compute the natural gradient, the gradient with respect to natural parameters of digital distribution, which is a good property, and we cannot always do it. So basically, we repeat the same algorithm we used for training skip-gram, and again, we can think that we are done now. There is nothing else to do. However, remember that we decided that we fix the same number of meanings for each word. Do you think it's a good assumption? No, it's probably not a very good assumption, because some words clearly have lots of meanings and some have maybe less. So what we can try to do, we can try to come up with a heuristic, with a good heuristic that will tell us, for example, based on the word frequency, how many meanings each word can have. This is a not too bad idea, because basically, well, there is a correlation between word frequency, well, how often it is used, and how many meanings it has. Usually, the more often it is used, the more meanings there is for each word. But it may be a bit non-trivial to find the right heuristic. We can also use some external knowledge. For example, we can take Wikipedia, find for each word its ambiguation page, and assume that Wikipedia users know everything about the current state of the language, that all the meanings listed there, they are the only meanings we need to discover, and use this. However, even so, modern external knowledge bases as Wikipedia get updated with some delay. Some editors may miss something, or if we have to train on something else, not Wikipedia, it's unclear how we will do it. So it's not really a remedy. Again, what we could do, we could use something like a part of speech tagger just to learn different meanings for different parts of speech, if the word may appear in different forms. But I don't think this would solve the problem completely. Or, and the rest of my talk will be about this, we can figure out something really smart, something that combines all the strong sides of maybe of all heuristics we can find. So this question of how many meanings words have is not very unique. I'm sure those of you who already practiced, some deep learning have already asked yourself, okay, how many layers I need to have in my neural network, right? Basically, the success of deep learning depends a lot on the right architecture choice. And one of the most important kind of structural parameters of the neural network is how many layers there are. And of course, you can say that if you train on a really large data set where there is no risk of overfitting, you can simply add as many layers as your GPU permits, something like this. But on many problems, there is a risk of overfitting. And in fact, even on ImageNet, I think some of the models already, well, you can see that some of the models already are overfitting. So it is important to use the right number of layers, not the biggest number you can afford. Another situation is, this example is maybe even more interesting because it involves not simply, a computational limitation or an overfitting problem. It involves our prior understanding of what the cluster is. So if you look at this picture, you see some data points on the plane, and there is a very simple question: how many clusters there are? Depending on what you believe the cluster is, you can see very different cluster configurations of this data set. Even though it's a very small data set, it's very simple, because you can say, oh, actually, all these data points, they come from the same very big white Gaussian. Or you can say, no, I actually see three small Gaussians here. Or you can see 5. Or maybe some algorithms can actually tell you that, well, each data point belongs to its own cluster. It is the situation where you have to explicitly define what you believe is the cluster, and at what point you have to split a collection of data points, one cluster into 2, let's say. So how do we answer this question traditionally, using traditional model selection process? So normally what you would do, you would assume that your data set is generated from a mixture model. And Bayesian mixture model, again, usually looks like this. You have a Dirichlet prior over cluster probabilities, prior cluster probabilities. Then each cluster has its own set of parameters. So here I'm using this slightly unusual notation. So I denote cluster parameters as phi. And by this, if this looks weird to you, I have, with gray font, kind of an explanation. So here, H, you can think of H as a prior distribution over cluster parameters. But it's important I use this notation. You will see in a second why. Then, after we generated our clusters, and we know a priori what point belongs to what cluster, in general, which cluster is more popular than others, for each data point, we choose the cluster from a categorical distribution parameterized by pi. And then, once we know the number of cluster, we can sample the data point. Oops, sorry, there should be x. We sample x from the cluster chosen by Zi. So basically, that's a traditional mixture model. And to estimate the right number of clusters, what do you usually do? Well, imagine you're only interested in the predictive performance of your model, so you simply wanted to know not overfit. Then what do? You enumerate all possible number of clusters, and until it doesn't fit into your memory. And you try to assess directly or indirectly this conditional likelihood, the likelihood of some validational data set based on conditioned on the trained data set, on the parameters of the trained data set. And this approach works, but at very least it is computationally inefficient. You have to try lots of different models. And it is also not very elegant. Because you have to split your data set into kind of 2 data sets. You have to make sure your validation data set comes from the same distribution. It is not always practical, especially if your data set is very big, as in this is usually the case, let's say, with deep learning. If you had to estimate the number of layers and had to try every architecture, that would be very, architecture with every number of layers, that would be computationally difficult. But fortunately, there is an alternative approach which requires a slight change of paradigm. So for this particular problem of clustering, we will do the following. So let us define an infinite model, an infinite mixture model. So this may sound unusual, but for a second, let's assume that we can represent our model as a weighted sum of delta functions. So our model will be a distribution over cluster parameters. There will be an infinite number of cluster parameters, each taken with its weight. And the predictions under our model have this form. So when we want to generate a new data point under our model, we simply choose, we basically have a mixture model using weighted according to our collection of parameters, and we simply choose the mixture component, and then compute the density under that mixture component. Then what we do is we choose a nonparametric prior for this mixture of clusters. And this will be the central idea of the next few slides. So we will be choosing a prior that is called Dirichlet process. So I'll do the following. I will not explain all the details of Dirichlet process because this is a non-trivial mathematical object, and to rigorously and properly define it, I will need one more lecture. But I will try to show you the interface you can use to Dirichlet process, and maybe through that we will understand it to some extent. So we assume that there are two objects, the base measure h. Remember, h is a prior over cluster parameters, and alpha. Alpha is just a scalar value. We will see what role it plays. And these two parameters parameterize the Dirichlet process from which we generate our model, our mixture of clusters. And then, if we could choose the right prior, then we could perform the model selection in one shot. Basically, when we need to generate a new data point or assess likelihood of a new data point, we simply compute this posterior predictive distribution, which is an integral or an expectation with respect to the posterior, to the model posterior. And as we know from Bayes' rule, the model posterior up to a constant is just the product of a prior and likelihood. So now you may want to ask a question, why couldn't we do the same here with a finite mixture model? The answer is that technically we can, but often it happens that even despite our best efforts in regularization, even if we choose the right priors, we may find a degenerate solution where, for example, each data point or maybe very small number of points are assigned with their own cluster simply because it explains this single point very well. And it's very difficult to come up with the right prior if you formulate the problem like this. But I will show you why it is reasonably simple to get a good prior if we think in this way. So what is a good non-parametric prior? What is a good prior over this infinite mixture of clusters that we think is useful? So I think it should have the following properties. So first, it should allow potentially infinite number of clusters. We should not restrict a priori complexity of our model. However, we should be smart, and if we have a finite data set, let's say if we have just n data points, then the number of clusters we discover in this data set should be significantly less than the number of data points, right? We don't want to be in this weird situation where each data point gets its own cluster. And another property we want to have is that we want the model complexity to grow as we get more data, which makes sense. For small data sets, only a small number of parameters should be enough to describe. But if the data set grows larger, and larger, potentially data comes from a non-stationary distribution, we should increase our model complexity. We should allocate more clusters. And this prior, as I already told, that we'll be working with that has these properties is called Dirichlet process. So I will not define what Dirichlet process is, but I will talk about its two representations. One is called Chinese restaurant process, and another one is called stick breaking process. They look very different, and it's difficult to believe they're actually the same thing. But I will try to explain maybe why they are connected and how they can be useful for our problem of discovering the number of meanings. So what is a Chinese restaurant process? So imagine you come to a restaurant and you're the first customer. The restaurant is empty. So what you do, you just take a table and you sit on it. Then the next customer that comes after you has a choice. Either they sit with you at the same table, or they decide to sit at a new table. Imagine they decide to sit at a new table. Basically, at every time step, a new customer comes, and it has a choice to sit at an existing table with a probability proportional to number of people already sitting at this table, or to take a new table with probability proportional to alpha, where alpha is that parameter of the Dirichlet process. So we allow customers to come one by one. We sample these table assignments sequentially, and this defines a distribution over partitions of natural numbers. So you can take the full infinite set of natural numbers and define, according to this process, a distribution over partitions over any finite subset of natural numbers. So how does it help us with our clustering problem? Well, we can treat these z variables the same way as we did in the finite mixture model, as cluster assignments. So we can say now that each table is a cluster, and for each non-empty table, we sample a cluster parameters from our prior age, and then when we need to generate the data points, we simply sample them from the corresponding mixture component using the corresponding parameters. So this is a Chinese restaurant process, and in fact, it is already enough to make our model non-parametric and automatically discover any number of meanings. Basically, the only thing we need to do is that we need to replace our old prior over meaning probabilities and over meaning assignments here with this nice prior defined by a Chinese restaurant process. So the Chinese restaurant process is basically, we're almost done here. The only problem is that data is not anymore IED. So this context that we generated here completely independently, we can no longer generate independently because these are all conditioned on each other. We generate them one by one. So this is not very convenient for stochastic variational inference, because in stochastic variational inference, we want to have something where we have either a sum of terms, and we can randomly sample terms from the sum, or an expectation. This would be much more convenient for Gibbs sampling. However, so we will not use exactly the Chinese restaurant process to define our model, but we will first note a few things about it that makes it very suitable for our purposes. So here, first, it is clear that even though it is possible that each customer may sit at their own table, which is an undesirable situation, the probability of this is very small, the prior probability, and it will be easy to discard. Second, it is also clear that this restaurant process has a clustering property. Richer gets richer. The more people sit at the table, the more likely the next customer sits at this table too. And this is a good property if we believe that the more often word meaning is used, more often it will be used again. So for some applications, it is a reasonable prior. And second, it is also, remember, we had an issue, we couldn't decide how many classes we should use, not because we cared about predictive, the predictive performance, just because we couldn't agree on what to treat as an individual cluster. So here, in this process, we have this parameter alpha that decides a priori how likely, with what probability we should create a new cluster. The larger the alpha is, the more likely a new customer creates a new table, creates a new cluster. And by tweaking this parameter, we can either increase number of clusters, increase the granularity of our clustering, or do the opposite. If we want only a few big clusters to be, we only need to set alpha to a small value. So because Chinese retrieval process, even though it is very intuitive to understand, and it's really simple to generate data with it, it is not very, as we just said, it is not very convenient for stochastic variational inference. And because we want to use stochastic variational inference for training our model, we will have to use something else. And this something else is stick breaking process. So how does it look like? Imagine you have a stick. So this stick has length 1, and we will be breaking it infinitely many times. And the pieces of this stick we'll get during this process will be our prior probabilities of meanings, pi. So how does it work? So at the beginning, I have the whole stick. Then I decide where to break it, and I do it by sampling a breaking proportion from a beta distribution with parameters 1 and alpha. So as you probably know, the support of beta distribution is numbers from 0 to 1. So we can interpret these numbers that we sample from beta distribution as proportions with which we should break the currently available part of the stick. So we decide where to break, and this part that we just broken becomes the prior probability of the first meaning. Then the rest of the stick has length 1 minus pi 1. Makes sense, right? We repeat this process, which we sample another stick breaking proportion beta 2 from the same distribution. Again, break the stick. This becomes the prior probability of the meaning 2. And we repeat this process infinitely many times. So the generative process, if we want to use it, this prior to define a mixture model, the generative process looks the following way. So first, we generate infinitely many betas, these stick breaking proportions, and we sample infinitely many cluster parameters. Remember, we want to have an infinite model. Then we compute these prior probabilities of clusters or word meanings using the following formula. So it's the proportion with respect to which we're breaking the currently available piece times length of the currently available piece. It is very simple to show that it's simply 1 minus the length of already broken pieces. Then, once we have pi, we can apply absolutely the same logic as in the finite mixture model. We can define a categorical distribution where the probability of each outcome is distributed according to pi. We sample the cluster assignment, the cluster indicator z, from this categorical distribution. And when we need to generate a new data point, we generate it from the cluster defined by z. So that's basically the same model. So what is interesting is that this infinite mixture model that we wanted to represent, this infinite sum of delta functions, is exactly distributed according to a Dirichlet process. And z, these cluster assignments, are distributed in the same way as if they were generated by a Chinese retrieval process, because they are all the same. So why is it so interesting? Remember, in Chinese retrieval process, customers came one by one, and we had to generate their cluster assignments sequentially. Here, we generate them as in the finite mixture model independently, even though they are distributed the same way. So this is a very interesting fact, and it is very useful because Chinese retrieval process is maybe easier to understand when you see this for the first time, but this representation is much more convenient when you need to define a mixture model and use it for Bayesian inference. So basically, we're done, and our skipgram model, our skipgram extension that can automatically extract the required number of word meanings, is based on the infinite mixture we just described. So potentially, we are able to learn infinitely many meanings. We are only limited by our computational power and the desire to learn too granular meanings. We can automatically perform model selection because we have a very, very good prior that does not allow us to do stupid things. And we have the control of mean granularity. We have this hyperparameter alpha that we can use to choose how many means we want to have a priori. And there is only one issue now. So we have an infinite model. And if we want to derive a stochastic variational inference algorithm for it, it looks like we have to deal with infinite dimensional things. Well, infinite dimensional things will not, yes? Do you have? You change your mind?
I don't understand how many times you're gonna sample from beta distribution. Like if you go
infinitely many times.
How come we can sample infinitely many times?
Well, at least in our imagination we can, right? For a mathematician, infinitely dimensional object is not a problem. But practically, I guess you mean practically, if we were to generate data, how we would do that? Yeah, that's a very good question. We will not be able to do it, and I'm now describing how we can avoid doing this.
Okay, thank you.
So if we want to derive a stochastic variational inference algorithm for such a model, as we just said, well, it kind of feels kind of complicated. We don't have infinite RAM, we don't have infinite compute. So we'll do the following trick. We'll actually use a finite dimensional variational approximation, and for this we will avoid the need to do anything infinite dimensional. So how does it look like? So first, as usual, we assume a fully factorized variational approximation. So we assume that all parameters are independent in our posterior. We still have infinitely many betas and infinitely many cluster parameters phi. But we say that there is a number t after which we don't care. So t is the maximum practically interesting number of clusters we want to have. We know usually we can set the upper bound. And for bt, we set the variational approximation to a delta function at 1. So if you remember the formula for prior probabilities over clusters, it has this form, and if beta t equals 1, it means automatically that all further betas are 0. So we will stop the stick breaking process, guaranteed, and it is guaranteed. Another trick that we do is that we say that, again, for all clusters after t, their prior distribution over beta k is the same as, their posterior is the same as prior, and the posterior over cluster parameters is again the same as prior. And let's see how it can help us. If we agree with this, then, well, first thing we can note is that, again, Q of B will be a beta distribution thanks to conjugacy. And second, the lower bound decomposes in the following way. So first, let's write it as we are used to, like as in DAEs, for example, they like to write it as an expectation of the likelihood, of the data likelihood, minus the KL between your posterior and your prior. Let's try to expand this KL divergence. So it will be, we can decompose it into two sums. The first sum is from 1 to t. So we enumerate all clusters from 1 to t, and we have this KL between Q of B and Q of phi and P of B, P of phi, and the second sum from t plus 1 to infinity. And because we set this, oh sorry, this should be Q. There is a typo. Because we set Q, the posterior for all succeeding clusters to prior, this scale divergence is 0, and we don't need to compute it. So even though our original model was infinite dimensional, when we're doing variational inference for this infinite dimensional model, we can use the finite number of dimensions. Does this answer your question? Yeah, good. And as before, we simply use stochastic variational inference. Now it becomes just the same lower bound as always, and we can use it to learn the model. This basically explains how you can apply this practically. So let's see if this works and it can do better than the standard skigram. So here in this table, you can see the model trained with different parameters of alpha, with different values of alpha for two words, light and core. we show the nearest neighbors to embeddings associated with each of their meanings. So the second column is the prior probability of a meaning. It should be, I called it P of Z, but it could be called pi. So the same thing that is generated by the Dirichlet process. And you can see that the standard skipgram learned just a single physical sense of the word light. As we increase alpha, we first get two different meanings. One, it looks like it is related to light kind of army units, and the other one related to the light as the light. And then if we slightly increase the alpha a bit more, we get much more meanings. So here we can get, I would say the poetic, the literature kind of meaning of light, the physical meaning of light as before. We keep this military meaning of the word light, and we get a few more. Same happens with the word core. So strangely, skipgram defines only one meaning that corresponds to core of a CPU. However, we are able to find the core of an atom and many other things. So this is very useful, and it does work. So we can ask ourselves, how many word meanings do we find when we change the parameter alpha? And here we plotted how many meanings we find based on the logarithm of the frequency, logarithm of how many the word appeared in the corpus. And you can see that, well, it roughly grows. You can also ask yourself of how the number of how many words had certain number of prototypes, and again, as you increase alpha, you get more words with many meanings. And the final result I want to show you is this argument about model selection. So remember we asked ourselves, basically it was not clear what happens if we let the skipgram to have twice as many dimensions. So will it be able to actually understand all of the meanings simply by measuring them into a single vector? Maybe possible. And you can see that indeed, if you increase the dimensionality of the skipgram model, it improves the likelihood. But Adagram, very quickly outperforms this twice as large model just simply by allowing words to be explicitly ambiguous. And roughly, to some extent, when you increase alpha, the number of meanings grows and the likelihood improves, but at some point it starts dropping. And the second column is, roughly speaking, the correlation between the word meanings that our model found in a supervised manner and the human labeled collection of ontology of word meanings. And you can see that here the behavior is slightly more stochastic, but again, our model, the multi-meaning model was able to improve on this score as we increased the number of meanings. So here I would like to end. So I presented the work we've done together with our colleagues at BayesGroup. It has been published at AI Stats 2016. And if you want to play with the model, you can do it today at the seminar. And if you want to download the source code and play with it later, you can find it at these links. Please, today, use the second link because it's a special version that it was adapted for this seminar. That's all. Thank you. Yeah, there's a question.
When you mentioned that the Chinese random process violates the IID assumption, and that's why you use the surrogate random process, does that mean that people who work on nonparametric Bayesian methods try to do the same thing? They look for other processes that don't violate the ID assumption, or there are other works or other methods to tackle this problem?
So I couldn't quite get it. What assumption? Sorry, can you?
So you said that the Chinese random process, there's a dependency between xi and xj, and that's why you used the stick break, right?
Yes.
So does that mean that people who work on nonparametric Bayesian inference always do that trick?
Well, no. So first, this sequentiality is only an issue for us if we want to use stochastic variation inference. If we want to have a single objective that is convenient to optimize. Otherwise, it is not such a big problem. And in fact, if you want to do Gibbs sampling, if you want to do MCMC, then Chinese decision process may be actually easier to implement and be more convenient. So I would not say that one is better or worse than another.
Okay, got it. Thank you.
So would it be possible to assign a hidden variable also to the target word, that word in the context that you're trying to predict? Because they might also have different meanings.
Yeah, that's a very good question. Yes, definitely this is something you can do, and ideally it's something you would do. The only problem is that it would make the inference process over word meanings very entangled, and you will no longer be able to do it independently for each kind of word and for each context. It will define a big graphical model, a very long, complicated Markov chain, which we'll have to do inference over. That you would like to avoid this, but otherwise you're certainly right.
Thank you for the lecture. Could you please explain one more time how does data helps to infer number of meanings? I mean, I couldn't get it.
Well,
there is like no parameters. I thought that it's some kind of empirical bias or something like this, but it seems that it's done somehow through the Dirichlet process. And could you please explain?
Yeah. So all the information about how many meanings are used in the model is encapsulated in G, in our model, which is a potentially infinite sum of potentially infinite mixture of model parameters. We define a prior that a priori would not allow us to have too many mixture components there, and how many we'll get is governed by this parameter alpha. Then we do posterior inference. We could do it exactly, but we are poor people, so we do variational inference, but still. We have a posterior distribution over these potentially infinite mixtures. And because the posterior is a product of prior and likelihood, the prior does not allow us to have too many meanings, and basically it regulates how many meanings we have. But likelihood is telling us, is this number of meanings enough? And so this is a traditional model selection, basically model selection by Bayes rule.